Now we're ready to learn and apply the idea of locality-sensitive hashing. We're going to do this first for the special case of min-hash signatures and later see the general LSH idea. First, let's remember where we've gotten so far. We converted documents to sets of shingles, and then we converted the presumably large sets of shingles to short signatures consisting of vectors of integers. We can compare two signatures and estimate quite closely the Jacquard similarity of their underlying sets. Since the signatures are relatively short, we can fit many of them into main memory at once and thus compare many different pairs of signatures without having to spend the time needed to read each signature from disk many times. The idea behind LSH is to look at the collection of elements, that is, signatures in our example here, whose similar pairs we want to find, and without constructing all pairs of those elements, create a short list of candidate pairs whose similarity actually must be measured. When constructing candidate pairs, we look only at individual elements, not at the pairs themselves. All pairs that are not candidates are assumed not to be similar, even though in rare cases there will indeed be false negatives, that is, pairs that are similar but never checked for similarity. For the cases of signature matrices, we perform LSH by creating some large number of hash functions. These are ordinary hash functions, not min-hash functions. For each selected hash function, we hash columns to buckets. For each bucket, we make all pairs within that bucket a candidate pair. A pair becomes a candidate pair if any one or more of the hash functions puts both signatures in the same bucket. We need to tune the number of hash functions and the number of buckets for each hash function so that the buckets have relatively few signatures in them. That way, there are not too many candidate pairs generated. But we can't use too many buckets, or else pairs that are truly similar will not wind up in the same bucket for even one of the hash functions we use. To start, we have to agree on how similar is similar. We pick a threshold t, that is, the minimum value of Jacquard's similarity for us to regard a pair of signatures as similar. That is, in the ideal world, columns C and D of the signature matrix M would be a candidate pair if and only if their similarity was at least T. Remember that the similarity of signatures is the fraction of components, or rows of the signature matrix M, on which they agree. So we want columns C and D to be a candidate pair if the fraction of rows I for which M of I and C and M of I and D are the same, to be at least T. So we need to create some number of hash functions and use each to hash the columns of signature matrix M into buckets. And we need a trick to make sure that similar signatures or columns are much more likely to hash to the same bucket for one of these hash functions than if the signatures are dissimilar. As we mentioned before, we're going to regard a pair of signatures as a candidate pair if even one of the hash functions puts them in the same bucket. So here's the picture of how the hash functions are created. The yellow area is the signature matrix M. Each column corresponds to one signature, and each row is one of the components of all signatures. That is, each row was created by applying to each of the underlying sets one of the min-hash functions we used to create the signatures in the first place. We divide the rows into B bands for some number B. As a result, there are R rows per band, where B times R is the total length of the signatures, that is, the number of min-hash functions we used to create the signatures. We're going to create one hash function from each band. Remember, we divided the signature matrix M into B bands of R rows each. From each band, we create a hash function. This hash function hashes the values that a given column has in that band only. Ideally, we would make one bucket for each possible vector of B values that a column could have in that band. That is, we'd like to have so many buckets that the hash function is really the identity function. But that is probably too many buckets. For example, if B equals 5 and the components of a signature are 32-bit integers, then there would be 2 to the 5 times 32, or 2 to the 160th power buckets. We can't even look at all these buckets to see what is in them at the end. So we'll probably want to pick a number of buckets that is smaller, say 1,000,000 or 1 billion. As we said, we consider a pair of columns or signatures to be a candidate pair if they are in the same bucket according to the hash function for any of the bands. Put another way, the only way we can be sure a pair of signatures will become a candidate pair is if they have exactly the same components in at least one of the bands. Notice that if most of the components of two signatures agree, then there's a good chance that they will have 100% agreement in some band. But if they have few components in common, then they are unlikely to agree 100% in any band. We'll make the mathematics more precise shortly, but that's the intuition. Given T, the threshold Jacquard similarity needed for pairs to be considered similar, we need to tune B and R so that most of the similar pairs are 100% similar in at least one band, but few of the pairs with a Jacquard similarity less than T are 100% similar in any band. The only constraint we have is that B times R has to equal the length of the signatures, that is, equal to the number of min-hash functions we used to create the signatures in the first place. Intuitively, if we make B large and R small, then there are lots of bands, and therefore lots of opportunities for a pair to wind up in the same bucket. And since R, the width of a band, is small, it is not hard for a pair to hash to the same bucket for one of the bands. Thus, making B large is good if the similarity threshold is relatively low. Conversely, if we make B small and R large, then it will be very hard for two signatures to hash to the same bucket for a given band, and there are few bands to give them the opportunity to do so. Thus, a small number of bands is best if we have a high threshold of similarity. Again, we'll make the math precise shortly. Before we go on, here's a picture of what one of the hash functions for LSH on signature matrices looks like. We see one of the B bands, the band consisting of R rows, of course. We also show the matrix consisting of 7 columns or signatures, and each of the purple rectangles represents the portion of its column within the one band we focus on. Columns 6 and 7 hash to different buckets. Thus, they surely differ within this band, so we are not motivated to compare them for similarity. That is, the pair 6 and 7 is not made a candidate pair by this LSH hash function. Perhaps columns 6 and 7 will hash to the same bucket for some other hash function and will therefore become a candidate pair. But from what we can tell, looking only at this one hashing, they do not form a candidate pair. On the other hand, columns 2 and 6 do hash to the same bucket, so 2 and 6 is a candidate pair regardless of what happens in the other bands. There is a good chance that columns 2 and 6 are identical within the band shown. That is, these pieces of their columns are identical. There is a small chance that these segments of these columns are not identical, but they just happen to hash to the same bucket. We will generally neglect that probability as it can be made tiny, like 1 in 4 billion if we use 2 to the 32nd power buckets. Let's look at a particular example to get a feel for how the probabilities of false positives and negatives work out in practice. We'll assume there are 100,000 columns. That is, we're looking for similar documents among a set of 100,000 documents. We'll assume signatures are of length 100. That is, we use the 100 min-hash functions to create the signatures. The signature matrix M is thus 100 rows by 100,000 columns. Notice that the signatures fit very nicely in main memory. Assuming the components of a signature are 4-byte integers, each signature takes 400 bytes, and the total space requirement is 40 megabytes. Now, let the similarity threshold be 80%. That is, we consider a pair of signatures similar if and only if they agree in at least 80 of their 100 components. There are approximately 5 billion pairs to compare, so we'd like to use LSH to avoid having to compare them all. Incidentally, if you don't see why 5 billion is the approximate count of pairs, the exact number of pairs of items chosen from 100,000 items is 100,000 choose 2. Which is 100,000 times 999,999 divided by 2, And if we approximate the 5 nines by 100,000, we get exactly 5 billion. In our example, we're going to divide the 100 rows of the signature matrix into 20 bands with 5 rows each. First, let's consider two columns C1 and C2 that represent sets with Jacquard similarity 0.8. Notice that because of the randomness involved in min hashing, the columns C1 and C2 may agree in more or fewer than 80 of their rows, but they will most likely have approximately 80 equal rows. Now, what is the probability that these columns are 100% similar in one given band? Well, the probability that they agree in any one row is exactly 0.8. Remember that the probability that a min-hash function agrees on two sets equals the Jacquard similarity of the underlying sets. So the probability that the two columns agree in all 5 of the rows of a band is 0.8 raised to the 5th power, or approximately 0.328. That's not a very high probability. But we have 20 chances to make the pair of columns a candidate pair. The probability that they do not hash to the same bucket in one band is 1 minus 0.328, or 0.672. Okay. But the probability that the columns fail to hash to the same bucket for any of the 20 bands is that value, 0.672, raised to the 20th power, which is a tiny number. It's actually this 0.00035. The chance that pair C1 and C2 will be a candidate pair is 1 minus that, or 0.99965. Put another way, the probability of a false negative, a pair of sets that have Jacquard similarity 80% but whose signatures do not become a candidate pair, is 0.00035, or about 1 in 3,000. Now look at a pair of sets that have Jacquard similarity 0.4. The probability their signatures are identical in a given band is 0.4 to the 5th power, or about 1%. The probability that their signatures hash to the same bucket in at least one of the 20 bands is surely no more than 20 times that, or 20%. That's not great. It means that among 40% similar underlying sets, there are 20% false positives, pairs of signatures we will have to compare, and yet we'll find that they are not at least 80% similar. But 20% false positives is bad, but the false positive rate falls rapidly as the similarity of underlying sets decreases. For example, for 20% Jacquard similarity, we get less than 1% false positives. We cannot determine the exact number of false positives because that depends on the distribution of Jacquard similarities among the underlying sets. For example, if most pairs of sets were 79% similar, almost all would be false positives. But if the typical pair of sets has a Jacquard similarity of a few percent, then there would be almost no false positives. A way to look at the problem of designing an LSH scheme from a min-hash matrix is this. We want the probability of two columns sharing a bucket to be a step function with threshold t equal to the value at which we regard the underlying sets similar. That is, if the Jacquard similarity S of the underlying sets is less than t, we want there to be 0 chance that the signatures will share a bucket for one of the hashings and thus become a candidate pair. However, if the underlying Jacquard similarity exceeds t, we want the pair of signatures surely to become a candidate pair. On the other hand, what does a single row of a signature matrix gives us? It gives us a straight line. The justification is the theorem about the probability of two min-hash values equaling the Jacquard similarity of the underlying sets. That's not too bad. At least the probability goes in the right direction, but it does leave a lot of false positives and negatives. That is, for a given threshold t, all of these are false positives, and all of these are false negatives. But when we combine many min-hash functions into B bands of R rows each, we begin to get an S-curve shape with greatly reduced false positive and negative regions. We're going to derive the function that relates the probability of two sets having their signatures become a candidate pair to the similarity S of the sets. First, if the underlying sets have Jacquard similarity S, then the probability that their signatures will be identical in all R rows of one particular band is S to the R. So the probability that their signatures will not be equal in this band is 1 minus S to the R. And the probability that their signatures will be unequal in each of the B bands is that raised to the bth power. Finally, the probability that their signatures will agree in at least one band is 1 minus that, or 1 minus the quantity 1 minus S to the R, all raised to the bth power. Okay. As B and R get large, this function increasingly resembles a step function. And the threshold at which the rise occurs is approximately 1 over B raised to the power 1 over R. For example, in the case B equals 20 and R equals 5, the threshold will be approximately the fifth root of 1/20th, which is about 0.55. Here are some sample values of this S-curve for the case we have been examining, 20 bands of 5 rows each. It's not exactly a step function, but it does get rather steep in the middle. For example, look at the values between 0.4 and 0.6. The rise from 0.4 to 0.6 is more than 0.6, so the average slope in this region is over 3. On the other hand, in the region 0 to 0.4, the rise is less than 0.2, and the same can be said for the region from 0.6 to 1. That is, the slope is less than 1/2 in both these regions. So a rough approximation to this curve looks like this. Okay. It's not exactly a step function, but much better than the linear function we got from a single row. So here's a summary of what we need to do to find sets with a given threshold T of Jacquard similarity. First, we need to decide on our values of B and R. As we mentioned, the threshold T will be approximately 1 over B to the power 1 over R. But there are many suitable values of B and R for a given threshold. The larger we make B and R, that is, the longer the signatures we use, the closer the S-curve will be to a step function, and therefore the fewer false positives and negatives we can have. But the longer we make the signatures, the more space they will take and the more work it will be to perform all the min-hashing. Then we must run the LSH to get the candidate pairs. For each candidate pair, we examine their signatures and count the number of components in which they agree. That way we can determine whether the similarity of the signatures really does reach or exceed the threshold T. We can rely on the similarity of the signatures truly measuring the Jacquard similarity of the underlying sets. However, if we want to spend the resources, we can go to the sets themselves after determining that their signatures are sufficiently similar. In some cases, the similarity of the signatures will overestimate the similarities of the sets that they represent, so it is possible that the two sets are not really similar enough. By computing the Jacquard similarity of the underlying sets, we can eliminate the false positives. Unfortunately, we cannot eliminate false negatives this way. If two sets have Jacquard similarity above threshold, but by bad luck their signatures never become a candidate pair, then we'll never look at this pair of signatures or their underlying sets.